Okay guys, welcome to chapter 21. We are leaving behind chapter 20, which is not a big part in the OCR course, but lots of interesting ideas. And what it shows you, now we're getting on to more straightforward stuff, is that what you learnt at GCSE was not quite correct. Okay, there's a lot more going on inside the nucleus than just the radiation. So we're going back to around about the 1850s, 1900s, where there was a lot of 1880s, 1900s, when most of the research was done on radioactivity. We're still doing research now, but what a lot of the big ideas that we're studying in the course come from there. So what you had at GCSE was right, but there's a bit more to it than that. So we're going to stick with our looking at our three types of radioactive substances. Alpha particles are our main radiations, but it's not radiation, they're particles. You've got radiation that is truly radiation, gamma, and then we have beta, which is actually, as we now know, comes in two varieties. Other aspects as well, the particle physics, you might want to think of it as radioactivity, but actually keep it simple, because this is all about the stability of everyday materials at this temperature. Okay, so the modern universe, the universe we're in now, not high energy physics. Okay, so what do you need to already know? Well, if you go back to your stuff at GCSE, you're actually not going to be far off. We're just going to go into a bit more depth really, and bring a few more clues in, a few more things that you need to have as part of your answers. So properties are the three main types of nuclear radiation, alpha, beta, gamma. We're going to look at that idea of the other aspects of it, because we're going to have to do some research, some practical readings on this, and therefore how can you be trustable with your values. And then we're going to look at terms of mathematics of it. Okay, and this again leads us, key ideas that run from the last chapter, mentioned in here, but they come together really in chapter 21. So let's just jump straight in. Kind of the background facts. So we've done parts of this already. We've talked about this last year, this year, all over the place. So let's just bring it together. So as we said there, a lot of the work is around about the turn of last century. A lot of work links in with the electromagnetic fields. So crucial point is, all of what we're going to talk about is ionising radiation. So that's your key issue, key focus, key idea from this topic. It's all about what it does, okay? And there's two ways of looking at everything. So are we going to look at what comes out, or are we going to use what comes out from atoms to find out what's happening and changing inside? It's going to be both, okay? So when we take readings, we're going to be taking readings of these, but actually, what is it that causes it? That's the idea that we're going to really get to. So, just hint up on this. There's a little bit more to it than this. So again, when we talk about ionising radiation, people kind of get confused. Obviously, it creates ions. Okay, so you're either going to add or usually lose electrons from your atom. So it then becomes chemically reactive. Okay, and that's our crucial bit. It's all about making chemical reactions. So what is the process that causes it? Well, some are quite benign. Fairly obviously, chemical reactions make a difference. So when you've got collisions, when you're breaking up your molecules in your endothermic part of the reaction, okay, that is going to have an effect on the structure of the atom. But this is quite low energy, relatively speaking. Okay, you're just knocking electrons off the outside, as are all of them, but we can get deeper in rather than just the mainly outside electron shells for chemistry. Okay, we can basically, I'll link with collisions because it's, some people get a bit confused with this or get a bit argumentative, but physical processes. We've got chemical reactions, we've got physical processes like friction. Okay, particularly noticeable with insulators. So if you rub a balloon on your hair, you are ionising the atoms on the surface of the balloon. Also, the atoms on the surface of your hair. We can, as we saw last topic, go deeper. We can really whack the energy up, and so we can have particle accelerators. Now they don't need to be, let's be really precise here, they don't need to be really big, deep, Stanford Linear Accelerator or CERN or Fermilab or any of those places. As long as you can make your particles go faster, so you can smash things into them. Okay, and that causes ions as well as other things depending on how much energy. So low energy, fairly high energy, and the last one is, of course, back to quantum last year, we can have excitation. Now, excitation is usually used for just jumping up energy levels, so we're going to go beyond excitation. So usually metal atoms, so I'm going to put metal in terms of our thing here. It's not quite true, it depends how much energy you got, as we saw with our last particle physics area, but extra high tension, okay, so really high voltages, we can excite atoms, but more usually upper and or radiation. Photoelectric effect, you shine light on it, it will work as long as it's above that threshold frequency. Okay, now we're going to link into and keep coming back to a certain property, so we'll do that at the end of this section, but if you look through the information here, it gives you a bit of an idea. So ionisation for biological systems is risky, but for electrical systems, well, if it's your phone, that's not very good, but you can use it to detect radiation, as we showed with these spark counters, and as you will do with radioactive experiments. So, different things, different ideas. We can do a count for radiation, or as we saw in the last chapter, we can actually start doing measurements by that idea of using magnetic fields. So here we have unusually magnetic field out of the page, so you can work out what charge the source has, plus or minus, and how big is it. Okay, so again, this is where I'm going to pick up. We need for this chapter, so not particle physics, you can get away with using the chemistry shortcuts, but in this chapter we actually need to talk about the actual charge. Okay, so be wary of that, don't fall into that trap. Okay, so that's why I've put it into bold in your notes. Okay, so what is going on? Well, we have our three types of radiation, so a little bit more detail. We'll go into them through the lessons and give you a bit more idea, but let's just come up with our top trumps approach and just pick up some of the details. So, alpha, beta, gamma. Firstly, just be a little bit wary when you're asked this question, because that usually traps people out. And they'll say, it is highly ionising, or damaging, or low penetrating. Well, what they're asking you is what it's made of. So just be careful when they say, what is alpha radiation, for example. So what is it? It's a helium nucleus. Quickest way of visualising what's going on. Or you can always say 2 protons and 2 neutrons. Okay, so either of those would do. That's probably easiest because it gives us a bit of relevance. Okay, now what we're going to use, and again we're going to just stick with the basics at the moment, so we'll use the chemistry simplified version. Its relative mass compared to the others is basically, and I will say approximately, it's not exactly 4, but we'll go with that. And relative charge, as you saw, was 2 protons, so we have plus 2 charge. Okay, so again, just breaking it down, what that means. So these two things together, along with its speed, will basically, in other words energy, will basically tell us how well it ionises things. Because this has a large charge, and it's a bit like a bull in a china shop, you know, being struck by one of these is probably going to hurt a lot more than one of these, and definitely one of those, etc. Alpha radiation is pretty ionising. Now, we just need to have this scanned in our head. So again, from GCSE, I'm sure you've kind of learned this. You may have heard damaging, but it's how well it ionises. Now, how can we tell? The cloud chamber pictures will get very straight because it's got a lot of momentum, very wide tracks coming through. Okay, so these fat, clear tracks show that you've created a lot of charges, charged ions for the water to condense on in a cloud chamber. So highly ionising means you get good tracks, which is good. Penetration ability is quite, again, low. Just that's about all we can say. We can give you some ideas, but again, it depends on so many factors. We know at GCSE, you said around about, if you had air, 5 to 6 centimetres is about as far as it would go. Now in this picture, again, a bit like the one I showed you last week, there's actually 2 energy amounts of alpha particles, so you can almost see, you should be able to see quite easily on yours, but maybe not on the video so much, but you have 2 lots of penetration. Fast particles get this far, the slower variety get this far, but very distinct. But of course it depends. If you've got a high density air on a high pressure day, the air particles are closer together, it will get less far. On a low pressure day or higher up in the atmosphere, it will go further. So it's all a bit relative. It's all down to number of collisions is a better way of thinking about it. Okay, in terms of protection, again, just to give you a bit like GCSE, that hint at things to think about, you know, what's enough to stop it going through? Well, it won't go through skin. It won't go through skin that's in good condition. Anything like climbing injuries that cause cuts, it can get into there more easily. Thick paper, again, be a little specific there. Tracing paper won't be enough. So when you learnt the GCSE answer of paper, bit vague. Okay? And then it has some typical, fairly typical examples. So radiotherapy is used to treat cancers because it's very ionising, so it can actually kill off cells. It does a lot of damage on purpose, which is good. But if it can't get through skin, you have to think about, you know, where it's used. So you wouldn't use it by shining alpha radiation, try to shine it through your skin to get to something, it wouldn't work. So we'll come back to that kind of level. Okay, now, slightly dodgy, again with the spec. Danger, I would say risk, because you cannot say it definitely causes a danger. It heightens the risk. You get a greater probability of something happening. Okay, but if it's outside of the body, it's pretty low risk because it can't get through your skin and so on. Obviously it can through eyes, things like that, so there's different parts of your body that it can get in. But if it was to get into your body, it's very damaging. Okay, so it's got high ionising powers, or ionising ability, perhaps might be a better word. And because of that, it can cause a lot of problems, both mutating your DNA, causing damage to DNA, which then forms next steps, or actually killing things off, changing chemical reactions, etc. Okay, so the whole host of things if it gets inside you. Litvinenko, you may remember the case, was a Russian scientist who was poisoned with selenium. No, it wasn't selenium, but it was something that was an alpha emitter, and the Russian Secret Services pointed him with a very small amount of this metal. It's toxic as well, chemically, but it was a very small amount, so it didn't affect him on that. It was the radiation that killed him slowly over several weeks in hospital. Quite a famous case. One of my ex-students was part of the suing the team that took the Russian government to court. So always remember that one. Okay, now just pick up on a little thing, because this idea of ionising, okay, that high ability to ionize, just be wary, it doesn't necessarily mean that it's high energy. These are the slowest, okay? So of all of the radiation types that we've got on the page, these are the slowest. So it doesn't always equal that idea of energy. Charge, mass, and energy come together to tell us whether it's highly ionizing or not. Okay, so that's a really important difference from just turning up the power in particle accelerators. Okay, beta radiation, we now know that it's an electron or positron. So it doesn't have to be a negative electron, it could be a positive electron. Usually we're going to talk about beta minus. Okay, so that's beta minus, but that's beta plus. Okay, so again, just be a little wary of it. It is an electron. It's much faster than alpha particles. But basically, yeah, it is a fast moving lepton. I'll put lepton in brackets just to link it into the last topic. But yeah, it's one of them. Fast moving electron from the nucleus. Okay, don't forget, these are all nuclear radiation, so they're all emanating from the nucleus, and as you know, leptons can't stay in the nucleus because there's nothing to hold them there. There we go. So, nuclear strong force doesn't apply. Its relative mass is a lot smaller, 1,840th. You know, its relative charge is minus E. I will put plus E in brackets as well, so it's only got half the charge. It's got an awful lot less mass, excuse me, bring them all in, awful lot less mass than the alpha particle. So because of that, it's actually quite a low ionizing ability, but I will say medium, just to keep it away from gamma radiation. Because it doesn't ionize much, and it's very easily deflected, so if you look at a bubble chamber, particularly, but if you're even looking at a cloud chamber, you'll see the tracks wander a little bit because they're ricocheting because it's very small mass. So bounces off, very thin tracks, quite hard to see, etc, etc. All linked back to the fact that it is low, relatively low ionizing ability. And because it doesn't hit many things and lose energy, its penetration is much more than the alpha particle. Going to go with medium though, just because it's nowhere near as good as gamma. Okay, so range in air, as we shall find out, obviously air particles, it will hit some, but it doesn't hit them as often, so it's going to go further. It's around about a region of 2 to 3 meters or so. Okay, what you can stop it by is basically, I'm just going to put aluminium. Now I will put thickish. It's not a very scientific answer, but a millimetre of aluminium or so, maybe half a millimetre, probably more than that, but thickish aluminium sheet. Now I won't say, you know, the idea of foil, so rather than aluminium plate, because that will definitely stop it, but how much can you get away with to stop it? So yeah, a reasonable mass. Again, we will try that out. Because of the fact that it takes a reasonable amount of atoms to stop it, if you have a few less atoms or a few more atoms, you get quite a difference at your detector. So if you had a detector over here and you're trying to count the radiation reaching it, whatever you put in the way will make a big difference. So because of that, it's quite often to find out thickness control of stuff, making aluminium foil for Christmas, for your turkey, for paper, etc, etc. So it's where some can get through. It's quite useful. In fact, it's a very useful form of radiation. It's also not as dangerous. It's not as risky. Okay, so in terms of its risk level, outside of the body it does go skin depth. Okay, so again, it won't go, if you're thinking about that, it won't go far into you. Your skin is quite thick, it's got multiple layers and so on. So it is dangerous on the skin. Subcutaneous, just underneath your skin, a bit of damage as well. Okay, how much lower is its ionising ability? Well, if you want to put a scale on it, around about a 20th. Okay, so 20th times as damaging as alpha. So 5% the issue, 5% the damage. However, don't forget, it's about where it can get to and damage, not just how much it damages. Okay, so if you were to swallow it, it wouldn't cause you much problem, it would still cause you a problem. Now, the third one is completely different, and again, as we shall find out, it's just like any other photon. Photons can have an effect, they can be absorbed, they can create things going on, so you can get excitation, de-excitation, different photons, and etc, etc. So just be wary of this picture. This will be certain frequency, this will be a second frequency at a lower frequency. F2 is less than F1. That's because it can be used to give energy to particles if it's high enough frequency. So we didn't do this last year, but if you've got a heck of a lot of energy in here, really high frequencies, then it can change things on charged particles. As we saw, it's linked in as a messenger exchange particle. But any energy that's left over is going to be re-emitted as a photon, de-excitation, and that will have less energy, so it will have less frequency. So you can link the whole ideas together with our last chapter, might make it more useful. But gamma radiation is by definition, oh, excuse me, he says the word and then writes another one, high frequency. There is no upper limit to this frequency, it's just the highest end of the spectrum. So, electromagnetic radiation, just like it was before. Okay, but really high energy, so therefore more problematic. Mass doesn't have any, because otherwise it wouldn't be a photon. A relative charge, it's not charged, as you well know. Does it cause damage? Well, yes, it can. It can still ionize, it can still cause ionization, but it's very low, it's low ability. They're actually quite hard to detect in Geiger-Müller tubes because they're actually quite poor at ionizing. Now, because it doesn't ionize, or it rarely ionizes, let's say that it's rarely ionizing, it's going to go further before it loses its energy. So it's got a really high ability to penetrate. It will go far. In air, again, infinite in theory, but realistically, in terms of its riskiness, tens of meters. Okay, so tens of meters. Excuse me, I'll change that. Meters. And notice the crucial difference in the phrasing here. Stopped by, slowed by. Now, I don't mean slows them down, but what it means is it will not stop gamma radiation. You cannot, because of its penetrating ability. So it's so difficult. So thick lead, we have to have multiple layers of lead and steel and concrete around where our sources are kept, because it will permeate that, and those are quite weak sources. But also, in terms of construction, usually it's in things like power stations and so on, so meters of concrete. Now, because it can penetrate, that's really good. You can penetrate through things, so we can almost use it like X-rays in some situations. We can use it for killing off bacteria, killing off living organisms, because that's quite useful. X-rays are used as well, I should say. And it also has lots and lots of different uses to basically trace where things are going, because the radiation will still shine through barriers. You'll still be able to detect it. Okay, outside of the body, it can cause you a lot of problems. The probability is low. Okay, again, that's the idea of ionising ability is probability, but it will penetrate through. So it will go through you. It can cause cancers. It can cause problems built up in cells long term and short term. The biggest problem from nuclear bombs that were dropped in Hiroshima and Nagasaki was the gamma radiation after the heat came out, after the energy got released. So in the body, strange enough, it's actually around about the same as beta radiation. So both of those are quite useful for medical purposes. Alpha is good if you want to kill off cells that are already cancerous. In some strange way of paradoxes, radiation can cause cancer, but it's also very good at killing off cancers. Okay, so it's a bit of a problem. But also we can't get away from it because these are natural and they are around us all the time. So it's worth bringing in, and hence the footnote at the bottom, there are many other types of radiation. Okay, the particles themselves, if you're splitting a nucleus, for example, the two halves of the nucleus come out fairly quickly. They recoil at high speed because of the energy released. But also lots of others that we looked at in the last topic. Okay, less common in terms of effect on humans, so less noticed, but anything, as long as we got enough energy, can make it happen. Its charge and mass makes the biggest difference to how well it works. Okay, final little bit of information, which is crucial because it brings us back to that first section, which I've tucked underneath. So let's just grab that out again, which is detection. So again, we did it earlier with electric fields, we did it with magnetic fields, but the key idea is we can detect the radiation by thinking about their specific charge. Okay, so as I said here, it's just simply charge per kilogram, but it's full units, it's not relative. So proton divided by the mass of a proton will give you a value excuse me, of 9.58 times 10 to the 7. It is really big. Okay, so that's tiny, but because that's tinier, you're going to get a big value. So charge to mass ratio is a really big version. So coulombs per kilogram, how much charge would 1 kilogram have? It'll be quite a lot. Okay, neutral particles, of course, have no charge to mass ratio. So in terms of my diagram here again, gamma source is undeflected. Gamma radiation is undeflected because it doesn't have charge, not because it's gamma. So anything without charge will carry on in a straight line in an electric or magnetic field. But the other bits come back to the equation BQV equals mv squared over r that you did with magnetic fields. Okay, alpha source, far less curly, bigger radius of curvature than these because it's got a mass of 4, so it's got more momentum, so it needs a greater force to turn it around the corner. And that showed up, I think, quite nicely there, so fast and slow. So you'll get a different effect. Please notice with all of these, because they're leaving a trail, they will all get a tighter curve over time as they slow down. Now the interesting thing, which brings us right back to J.J. Thomson, is if you look at the value for an electron, because its mass is so much smaller than that, its number is so much bigger. So it is 1.76 times 10 to the 11. Again, you don't need to memorize these because you can work them out dead easily. Way bigger. So if you go back to a magnetic field track, huge curve, tighter curve. The tighter the curve, the greater the charge to mass ratio. Okay, because it's the charge that pushes them around. The mass makes it difficult to turn the corner. So bigger the value for charge to mass ratio, the more curly the track. And it was this that J.J. Thomson found out, because the proton is the nucleus of a hydrogen, the light of hydrogen atoms. It's the lightest known element at the time, which is the lightest known element now, sorry, the lightest known particles of the time, and therefore it was staggeringly different, and that's why he spotted that pattern. So, do we need to work that out? Well, yeah, or more often it'll be for our pictures, it'll be the curving effects of alpha and beta and other such radiation. So they'll often be not just the proton or the electron. Worth pointing that the specific charge of any of the ions is way less than specific charge of particles, of individual particles. Okay, so yeah, if you had a value for ionized magnesium, okay, then you'd only necessarily have a charge of 1 or possibly 2 lots of charge divided by much larger mass. Okay, so again, not tricky stuff, but its meaning is quite important, especially when you're thinking about how you're using it to detect what radiation is coming out. And the most useful way is, as we've already covered in several chapters, electric fields, magnetic fields. Magnetic fields because they're nice easy circles and the maths is easier. Okay, we'll finish there. Cheers.